One of the things about ELISA is that when they think about possible sources, things that are stellar mass, so instead of the supermassive black holes and such things, are usually have been thought to be combined or limited to the galaxy, because we usually look at white dwarf binaries. But, and this is sort of the pre-conclusion, higher mass black holes, it's possible to actually, with LISA, detect them at extragalactic distances. This does not mean gigaparsecs, and not even hundreds of megaparsecs, but it may be possible. So what I want to kind of figure out is, what can we learn? So what I'm going to do, since following Pow's instructions, I'm going to make this first a little tutorial on LISA, then a little tutorial on dynamically formed binaries, because that's, despite what Salvo said this morning, I think dynamically formed binaries are probably more likely to be LIGO sources than the common envelope sources. But, quick summary of ELISA. This is a one-slide summary. So what ELISA is it will be 3 spacecraft following in the orbits that I kind of have shown here. Let me do a little better. So if you look at this little orange spacecraft follows this line, which is a perfectly independent elliptical orbit around the sun. And you take 3 spacecraft, put them on slightly different orbits, and what they end up doing is forming a little triangle of satellites, a constellation, that goes around the sun and tumbles as it's rotating around the sun. Okay, and it's at an angle of about 60 degrees to the ecliptic. Okay, laser links between each pair, okay, although current plan is just between 2 arms. If the Americans can finally come up with some money to help the Europeans, we might buy them a 3rd arm, at which point then you could create 2, yeah.
But injecting 3 objects in such an orbit, has it been done before? A similar exercise in terms of accuracy?
No, not that I know of. But we don't have to be that accurate. I mean, these things are going to be 10,000 kilometer changes in arm lengths during the orbits. So this is not really an interferometer in some ways. We take lasers from one spacecraft, lasers to the other, and then we beat the signals against each other. And if you've done anything in the workshop or the class before this on interferometry, you know about fringes that you would look for to see whether or not you had a change in length. Those fringes are flying by at megahertz range. And so what we measure is the rate at which they fly by. Okay, so we don't have to be that accurate. Currently, the plan is 1 million kilometer arm lengths, although I have heard 2 million kilometers floated occasionally. The old LISA plan was 5 million kilometers. What's impressive, because many people seem to think that LISA's been delayed and delayed and delayed, but really the moment at which LISA got selected as a ESA L3 mission was the moment that it was actually a real mission. The other 20 years prior to that, we were just hoping. But now we have a real mission, and scheduled launch right now is 2034. Now I want to talk briefly just about the noise sources that we have with LISA. This down here is basically stray accelerations. So it's an acceleration noise. It's force coupling from the proof masses in the spacecraft to the spacecraft, and it basically scales as 1 over f squared. Then at the bottom down here, this line coming across here is what we call interferometry noise. It consists of a bunch of different noises, but the most important one is shot noise. And I don't know if you know about shot noise, but effectively that is you're measuring a rather small number of photons. And so they don't all come at the same time. You get some bunching, and so you can get changes in brightness that just have to do with the statistical nature of the photons coming in. Okay. And that covers this flat range, and if you've ever looked at a LISA noise curve, you note the little wiggly bits here. Those are not an increase of noise at high frequency. What that is a decrease in sensitivity at high frequency. So if you actually look at a true noise spectrum from LISA, you would get this line and a straight line going out there. But what would happen is binaries with frequencies around here would be less sensitive, so that, say, a signal strength of 10 to the minus 17 might appear as though it had a signal strength of 10 to the minus 18 just because of lack of sensitivity. So that's a basic quick summary of LISA and how it works. The frequencies, just to talk about them down here, it's in the millihertz range up to about 100 millihertz or a decihertz. So that's the basic range where we're looking at. That pretty much eliminates all of the in-spiral merger of stellar mass objects that we've talked about in LIGO. So what we're going to look at is some different sources. So, first thing I want to say is what's so cool about gravitational wave astronomy is gravitational waves probe the dark phases of any stellar evolution. So when we want to create these double black hole or double neutron star binaries, and we want them to spiral in together, there's a phase where they're not going to be visible electromagnetically, and they're not going to be visible any other way except through gravitational waves. We see them later, perhaps when they merge as gamma ray bursts or something like that, but there's a dark phase that stellar evolution predicts. Okay? So now I'm going to just quickly go over the basic sources for ELISA so you know about them, but then I'm going to focus only on the stellar mass objects. There's supermassive black hole binary end spiral. This is a case where ELISA will be using pretty much the numerical relativity stuff that Deirdre was talking about. Because it's scale free, you can just scale it up with the masses, and we can do supermassive black hole end spirals. We have extreme mass ratio end spirals. In these cases, you have a supermassive black hole in the center of a galaxy, and small compact objects go in and get trapped in orbits around them. So you have a mass ratio, the Q that we've been talking about, that instead of being 1 or 10 or 100, these can be up to 1 million. So you could have 1 million, 10 million solar mass black hole with a 10 solar mass black hole in orbit around it. And then there's the stellar mass binaries in the local universe. And what we mean by those mostly is white dwarfs that are born in the Milky Way. There's about 30 million of them that will be in the LISA band. What's nice about them is they're simple, continuous, and they have a very small frequency shift. So when you think about most of what we've talked about today, or this workshop, has been how you get high fidelity waveforms so that we don't miss them. Sine wave. It's just a sine wave for these. Now, they will have slight frequency shifts, but only at the high frequency end, where we might be able to start seeing some small shifts. Okay, so what's beautiful about this is then the detection really isn't a matter of trying to match the waveforms exactly. It's just, do you have something that you can pull out the sine wave from? And if you're lucky, can you measure the small frequency shift? And why I say if you're lucky for the small frequency shift is that there's a clever way of determining distances. Okay. You can also do this with the end spirals as well, but this is a much simpler way of looking at it. If you measure the gravitational strain from a simple binary, the amplitude of it scales as assorted G's and C's, and then the chirp mass, omega, is the orbital frequency, and D is the distance to the binary. Okay. But effectively what that is, it's the strain, which is the square root of the power. For those of you that are astronomers, that's like the apparent magnitude. Okay. On the other hand, when you measure the chirp, you're measuring the precise loss of energy of your system. So the chirp, which is the frequency shift that I have there, is omega dot. Notice that it depends on exactly the same factor of G and exactly the same factor of the chirp mass and a different factor of the frequency. But thinking of it as an astronomer, it's telling you exactly how much energy your binary has lost, so it's just like the absolute magnitude. And every astronomer knows if you know the apparent and the absolute, you can measure the distance. So this bottom one down here is just the measure we can get for the distance. Measure your strain amplitude, measure your omega dot, measure your omega, and stuff them into that formula. And what you have is a measurement of the distance. And this is a very cool thing because we can start measuring distances. We can extend our distance ladder. Yeah.
Little h is the other constant?
No, little h is just strain amplitude.
Oh, sorry.
Yeah, so I mean, it's just what you'd measure in the detector. Yeah. And this is sort of a hand-wavy argument. The real argument's a little more challenging. So, I want to talk briefly about stellar mass black holes now, so we'll have a little lesson about them. They are, at least for ELISA, or ELISA, they would be the brightest sources from stellar evolution. In other words, the brightest gravitational wave sources that you could see from stellar evolution, for the simple fact that they're going to have the largest masses. And really, that's about all you need to worry about, because in the LISA band, we don't worry about merging or in spiral, so these are just sitting at a single frequency. So what you're really looking for is the mass, chirp mass. They are likely to be chirping a little bit, which is really cool, because that means we can measure distances. But unfortunately, they're very hard to make in large numbers in the field. This is something that Salvo talked about this morning. And one of the pop synths that I've done with Chris Belchinski, basically 99% of your binaries that will become neutron star, double neutron star binaries or double black hole binaries, will die in the first supernova. They will be disrupted. Of the remaining 1%, 99% of those will die in the second supernova. Okay, so they're very hard to create in the field. This is why you have to go out to several gigaparsecs or a gigaparsec to start seeing them with LIGO. But they're not so hard to make dynamically in dense stellar systems, and I'll have a little more discussion about that in, I believe, the next slide. They're likely to be more massive if they're formed at low metallicity, and what this generally means is old stellar populations. So older stellar populations will likely give you more massive black holes, and this pretty much narrows us down to globular clusters as wonderful sources of gravitational waves from black holes. So how do you make a binary black hole in a globular cluster? This is a cartoon, and there's no math involved in it, and much of it is conceptually right, but other than that, not all that correct. So at birth, for globular clusters, this is thought to be about 10 gigayears to 12 gigayears in the past, so about 1 billion years after the birth of the universe. You will get a cluster of stars that are formed out of a massive cloud of gas. Okay. The size, the masses of them really has nothing to do with where in the cloud, so you can just sort of this random distribution, and I've kind of drawn some big stars, which are implied to be massive, and little ones that are low mass. What will then happen is they will mass segregate, okay, through a process of a variety of processes, but basically it's exchanging interactions, because in a globular cluster we can have densities of stellar densities of 1 million stars per cubic parsec down in the center. Okay, so we have much higher densities. Collisions are actually possible, but flyby interactions are very, very likely. And what that tends to do is it gives kinetic energy, or gives speed to the low mass stars, takes it from the high mass stars, so they sink to the center. Once they sink to the center, they can blow up and become black holes. And so here's a little cartoon that now the big stars have turned into black dots. The big black holes, since they sink into the center, they're still having many interactions, and you can lose energy through interactions with other stars. They can form binaries dynamically. And the way basically that's done is if there's a binary of low mass stars and you bring a higher mass star into it, they'll form some big ugly three-body interaction for a while, and the low mass object is more likely to gain the most velocity and get kicked out. So you can start out with a binary system of 2 low mass stars, it encounters a black hole, and now you'll have a binary with a low mass star and a black hole. 2 interactions, you got a double black hole binary. Yeah?
Scale for the mass segregation much faster than the stars becoming black holes? So is that the chronological order in which things happen?
Not necessarily. It depends on the initial density. Oftentimes it's the black holes are formed first, and then they sink. But it depends. I'm looking at Pau because he's done this before. So, and then the final thing is that once you get this, the black holes are all interacting with themselves, and they can have what I call dynamical injection interactions. In which case now one black hole interacts with a binary black hole, the 3 of them form a 3-body system, and eventually they all end up with enough velocity so that you eject the binary and eject a single black hole. So what we're talking about here is, although I say globular clusters as sources of black holes, the black holes are kicked out. Okay. And then they just stay around their galaxy. So that's the basic idea of what I have for creating these black holes. And if you're at low metallicity, as we'll show in a couple later slides, you can get black holes with masses of 40 or 50 solar masses. In fact, one of the problems I have on my simulations right now is I'm getting runaway collisions, so I'm getting 800 solar mass black holes.
But are these the ones that will arrive with non-vanishing eccentricity at merger?
No.
I hear yes, and you say no.
The ejected ones, no. The bound ones, yes. Well, but I'm looking at Pau behind me, but the reason why I say that is the ejected ones will be ejected with fairly high eccentricities, but most of them are ejected the first 10 to 2 gigayears. And so now they have a long time. I mean, so there will be ones that perhaps right after they're ejected are very tight, and they'll be highly eccentric when they merge, but the ones that you give 8 billion years to coalesce will not. So my assumption is they'll be mostly circular. The ones inside, because some of them will stay inside your globular clusters, those guys will be eccentric.
Because they will interact again with all of them?
Right. They'll have interactions that tend to, we call thermalize the eccentricity. So, the next part would be, now that I can make black holes, how far away can I see black holes? So I wanted to do a little test to how distant how distant could these detectable binaries with LISA be. I gave this to an undergraduate as an undergraduate project. We took 10 million black holes, binaries, just because that was a big number. We did a uniform distribution in a 30 megaparsec sphere. We did a uniform distribution in masses from 10 to 80 solar masses. And I did a uniform distribution in orbital periods below 2,000 seconds because longer orbital periods than that are more likely to be blocked by the white dwarf binary population in the disk, meaning that they'll be hidden behind that noise. And then uniform distribution and orientation, and then we run all 10 million of these things through a LISA simulator and say anything that has got a signal-to-noise ratio above 8 is detectable, and that's 8 in a single detector. If we got that third arm, you would have 2 detectors, and so you could look at a higher signal-to-noise ratio from the 2. But in any case, what this plot is showing, and I may have to point over on this side, that color scale is the probability of detection. It goes from 0 to 100%, so this sort of aqua green yellow is about 50 to 60%. Along this side down here, this is the chirp mass. This is sort of the important one I want to talk about now. It goes from 0 to 70. And this is the distance in megaparsecs. Out here is at 15. So if you look at this, you say chirp masses between 20 and about 40 have a 50% chance of being detected at about 15 megaparsecs, which now gets us out to a really fun distance, because that's about where the Virgo cluster is.
And why LIGO didn't detect it already?
Oh, with LIGO's current upper bounds, that you would expect there to be 50,000 of these systems. You could have, I mean, actually I think 200,000 of these systems.
These are at a different frequency.
Yeah. Yeah, see, the point is these take forever, and what happens is they evolve in the orbital period. They speed up as they get to higher frequencies, so thousands of them sitting down here will give you the event rate that LIGO could see. So yeah, that was the first thing I did after this was, they're not 10 million. If you're asking that I think there are 10 million of them in the local universe, no. This was just to get enough statistics to get a decent, so this was just a quick parameter study. Okay. So then we said, well, what about population of field binaries? Because these are the ones anyway that we would expect if we didn't look at dynamically formed ones. So this undergrad project, Jesus and Hinojosa did, basically we used a gravitational wave catalog that actually was produced, I think, for LIGO by some LIGO guys. But this is all the galaxies. It's supposed to be effectively complete galaxy population out to about 30 megaparsecs, used synthetic universe, produced a bunch of field binaries. This is from one of Chris Belchinski's models. Populated the galaxy. This is sort of the three-dimensional view of the galaxies. Each dot is a galaxy. The big clump over there is the Virgo cluster. And then we said, let's see how many of those, using a real population, would be detectable by LISA. And in the stuff we did, we used percentages because less than 1 is really depressing. So, so what we had is that in elliptical galaxies, there was none. There was 0 to be detected. For the entire population of spiral galaxies out to 30 megaparsecs, you had a 96% chance of finding 1. And for the elliptical galaxies, only about an 82%. So if you think about it in some ways, if we're looking for dynamically or field-formed binaries, less than 2 is what you can expect. Okay. So now we look at binary black hole production in globular clusters. I mentioned the cartoon method of doing it for anybody that's interested in looking in more detail. I just went on ADS and did a Google or a search basically for any paper that had the words dynamically formed black holes, and I got these. So that's just a sampling of the papers. If I missed anybody's paper, that's just because you didn't come up quickly on my ADS search. Okay. Now, out of all of these, most of them have been studied as expected advanced LIGO sources, so there's a lot of papers there. A paper by Jonathan Downing and myself and a couple others found that actually some of the more massive black hole binaries that were ejected could in fact be detected by LISA, and that's what started this whole project for me, and we confirmed it, as I showed before, with that parameter study. Okay. So these are also in fact a paper just recently out, I think by Carl Rodriguez was talking, and Fred Razio's group was discussing these as LIGO sources. There we go. This is just some results from our simulation. I just want to show a little bit here about the low metallicity leads to larger chirp masses. The higher chirp masses gives a larger search volume, which is really nice. And what we have here is the top 8 things are different models with solar metallicity. They're showing the time at which the binaries have been ejected in gigayear. It goes from 5 to 15, or 0 to 15, and then the chirp mass. And you can see with the metallicity that you would expect to come from binaries in the field, the solar level metallicities, we get a nice, pretty much flat range of ejected binaries right at around chirp mass of 10, which is what you guys expect in LIGO. But if we go back and look at the low metallicity ones, you see we first have a lot more ejected binaries, and that's what we expect from globular clusters. And most of them are in that 25, or we have going up to 25 solar mass chirp masses. Okay. So that's in the range where we could detect them. This is from our paper in 2011. This is some work that Megan Morsher, Fred Razio, and Carl Rodriguez did at Northwestern. This is more recent, using a more sophisticated Monte Carlo code. And again, just want to point out, right over there, the little black dots, those are binaries with not chirp masses, but individual masses where the M1 is about 25 solar masses and M2 is 40. Yeah. Yeah, the question was, why does low metallicity imply higher chirp masses? The basic idea behind it is that at low metallicity, the atmosphere of the star has lower opacities. So that means you have a reduced stellar wind, which means you retain more of the mass by the time it goes supernova. Yeah. Okay, so, and the rest of these just showing some of the eccentricities. This kind of answers Pablo's question. The range of eccentricities goes all the way to 1, but when they're ejected, they tend to merge at circularized. And then some recent stuff that I'm doing with my grad student has also done this. This is 10 different globular clusters that we've done with the same low metallicity, rather high central density. And again, if we look at the chirp masses, each one of these colors is a different histogram. I found no way of doing it graceful, so that's the best I could do. But effectively, again, if you look at that, that's for an individual globular cluster over 10 gigayear that we expect somewhere on the order of 20 ejected black hole binaries with chirp masses around 20 to 25, which would be detectable out at the distances of the Virgo cluster with a 50% chance probability. There's still a lot more work to do on this. This is my grad student, so he still has to figure out some other problems to deal with this, but this is his research project. So now I want to shift gears a little bit and say, I hope I've convinced you we can detect them. Now what could we learn from them? What could you do with it? So with a reasonable signal-to-noise ratio, a LISA error box is about a few square degrees. So what I did here is, and it doesn't show up as well as I hoped it did on these slides, but this is a sort of finding chart of the Virgo cluster. So every one of those little blue dots and red dots and yellow dots is a galaxy. And that little dotted line, let me just go ahead and amplify it a bit. Are we going to try to make it dark? There we go. That's good, because that'll make the next one work as well. So this little dotted circle there is sort of like the LISA error box, although it could end up being slightly banana-shaped. Okay. So let's zoom in on that. That's where we might say we found a globular cluster, or found a black hole binary. Okay, so here's zoomed in, and if you see that, there's one big elliptical, that's NGC 4365, a couple little spirals in the background, and doesn't look like there's maybe one irregular. Okay, so we'd be able to say whatever we saw, that black hole came from that area. So now we want to zoom in. That is that galaxy. It's an elliptical galaxy. Every one of those little white dots they look like white dots, but they should be circles, is a globular cluster. Okay. This particular one, from their estimate, is that it has roughly 6,500 globular clusters.
Can you resolve the globular cluster?
In gravitational waves? No.
In optical?
Sort of, they circled them as little dots, but that's about the best you can do.
How do you make an argument that's
Not a star is the spectrum. Because if it was a star, you'd have a stellar spectrum. Here you have a clump. And you get a much broader spectral lines because of the velocity dispersion. So it's mostly from the spectrum. But this is just... Um, yeah, you should be able to throw out the distant ones. Is that what you're saying? Or yeah, well, that's the idea. Is what I would prefer to do is the other way. In other words, to say we measure the distance to the source using the gravitational wave method of measuring distances, and get a refined distance to the galaxy. If you can say it's got to be one of these big ones here. Yeah, but you could do the other way as well, because I presume what you're saying is knowing the right. Yeah, yeah, you could do that. So you're using your redshift. Right. And the reason why I kind of prefer the reverse direction is that in some sense there's a little extra science that gets there. Because the redshift is going to be a little bit contaminated by the phase distribution of your galaxies, right? If it's falling away from you, you're going to get the wrong distance. It's falling in toward the cluster center. But yeah, you could use that to refine it a little bit better. Although, given the fact that the ranges are only about 15 megaparsecs up to about 17, you're only kind of probing the front edge of the Virgo cluster. Yeah. So now, in what I presume is about the next 5 minutes or so that I've got, I have 10? Okay. Well, I want to make sure Pablo gets a chance to talk. So, I'd mentioned a little bit about, at low frequency end in LISA, I said there's the 30 million white dwarf binaries. And those 30 million white dwarf binaries, at the very low frequency end, when we're down to 10 to the minus 4 hertz or fractions of millihertz, that you can have tens of thousands of binaries in each resolvable frequency bin. So that means that you cannot individually resolve all the binaries that are in there. The ones that are very close might be very loud and stand out in front of it. You could pull those out. But eventually what you're going to have is just a confusion limit of all the different binaries, different distances, different phases, and all the rest of that, but within that frequency bin. So what we have here in this picture is the little gray dots are from population synthesis of binaries we could actually resolve, so we could pull them out. The triangles are known binaries, so not ones that come from PopSynth, but ones that we really know in the galaxy. And assuming you could do some of the best data analysis on the planet and pull out 20 or 30,000 binaries out of this population of 300 or 30 million, the little dotted lines that we have among config 1, config 2, and config 3, you see little dotted lines that are kind of rising among those. That would be effective noise that had nothing to do with your instrument. It was the confusion noise of the 30 million binaries. The standard analogy people like to use is, imagine you're in a large party, cocktail party where everybody's talking, and in the background you hear sort of this constant murmur. The people near you can understand what they're saying, but eventually once you filter that out, all you get is this constant murmur. It's like a noise, and that's what we have here. So this can be a problem if I'm starting to look for, if I want to get down to a millihertz, which is right down here. And remember, that's when I said the orbital periods of my black holes are, and you can see that's right in the mess of this confusion. So is there a way we can improve our chances? So what I have here, because it turns out there is, otherwise I wouldn't have brought this up. What we have here is the sky map of LISA sensitivity at an instant in time. Okay. The red is where we're very sensitive, so that's where the antenna pattern is pointing. The blue spots, the very center of the blue spots, are these actual places where LISA is completely insensitive to a gravitational wave. It would be one running along, just along the bisector axis of the arms.
Wouldn't that change with time?
That's why I got a movie. Okay. So this is over the course of a year, that's what that does. But the sort of interesting thing about it is those little blue dots follow figure eights. Okay. So there's going to be little figure eights in the sky. There's going to be 4 of them, which are going to have reduced sensitivity compared to everything else. Nature is incredibly kind. This plot here that I have here is the Milky Way, where I took one of my 30 million white dwarf binary PopSynth. I took LISA's 1 square degree, I was being optimistic, 1 square degree resolution, counted how many binaries were in each square degree, and added up their gravitational wave power, or signal in quadrature. And what you see here, again, So this is the center of the Milky Way. There's the path of the Milky Way in ecliptic coordinates. The little white figure of 8, if you're very clever and you launch LISA in the right orientation at the right time, you can set that figure 8 up so that you'll notice that that null runs right across through the center of the galaxy, which is where most of the gravitational wave sources of the white dwarfs are going to come from. So it's kind of neat. If you pick your orientation of LISA correctly, you can actually suppress the noise of the galaxy. So that sounds really cool. We were all excited by that. And then we said, so now where's the Virgo cluster? And it's right over here along one of the other lines. So at first that seems bad. But what we noticed is that if you looked at the way those figure 8s were doing, they were out of phase. And so if we actually look at the sensitivity to the galactic center and the sensitivity to sort of the arbitrary center of the Virgo cluster that we picked, they are out of phase. So that if we look at this picture, the blue is your sort of rough measure of sensitivity to the Virgo cluster, the center. The red is the measure of the sensitivity to the galactic center. So when we've fully suppressed the galactic center, right at t equals 0 over there, you're at maximum sensitivity to the Virgo cluster. It's very, very nice. So nature was cruel by putting the Virgo cluster there, but nice by making it 180 degrees out of phase. So that whenever the galaxy is too noisy, we don't see the Virgo cluster, so we don't care about the noise. And whenever the galaxy is suppressed, we see the Virgo cluster and we get better signal out of that.
But there must be signs of that noise. I mean, why would you like to suppress it?
Well, personally, I think it's the best science, but you don't really suppress this in some sense. We drop it down a little bit. It turns out it's really, when you average over the entire observation, it's about a 10% decrease. So it's not like you're losing most of these, 10 or 20%. Okay. So this is kind of a nice little feature that you can sort of look at different regions in space. So now I'm going to finish off with the science payoff. So I've talked kind of like how this can be done. What's the cool things we can get out of it? Number one, possibly identify the host galaxies. Important to realize, and I've given this talk at astronomer workshops, where the astronomers think that I can somehow identify the individual globular clusters. Not a chance. In fact, in denser regions of the Virgo cluster, I might not even identify the host galaxy. But the very big ellipticals that are relatively isolated, that have tens of thousands of globular clusters in them, those ones might be detectable. And if that's the case, you could possibly identify the globular cluster properties, in other words, the whole population of globular clusters around that single galaxy that may give rise to dynamically formed binaries. We can identify the mass distributions if we get substantial numbers of them. If we can get 10 to 20 of these black hole binaries, we can start figuring out whether or not they really are dynamically formed. Because one of the things that was in the paper by Carlos Rodriguez was this idea that even with LIGO, you could determine whether they dynamically formed or not through the spins, but through the masses. Okay. Because the only easy way to form these big, massive black hole binaries would be dynamically. So that's one thing that would be nice. And finally, the idea that I'd mentioned is getting the distances to individual cluster member galaxies, because it might give you a way to start to understand, in some ways, by matching the distance you get from gravitational waves with the distance you get from the redshift, to be able to see what is the dark matter distribution by understanding what the virial speeds are of the galaxies, because you know where they are and compare that with their redshifts. So that's sort of some of the possible science payoffs. That's it. Thank you. Tao's ready to jump on me.
We have time for a couple more.
Matt, why are you looking into roller clusters? I mean, if you want to look at binaries, self-imposed, and you want to keep them in the system, you should look at the nucleotide clusters. The velocity dispersion is much higher, so the retained fraction is much, much larger. So you don't keep them away, you keep them in place. So you should look at what?
The dense nuclear clusters of galaxies. Why do you not look at? And that's a reasonable place to look as well. But in my case, the idea is that the ones that stay in the nuclear cluster are more likely to be eccentric
So,
and perhaps harder to find.
but probably they're going to stop that. So why would you disregard them?
Because I study globular clusters. So, I mean, no, I didn't disregard them because I don't think they're viable sources, but I do think that in some ways the globular clusters are going to give you cleaner systems, and that's primarily what I'm looking at. By cleaner, I mean going to be ejected 10 billion or 8 billion years ago and then just coalescing. Now, I don't know, you can correct me on this because you know more about galactic centers, but what's your metallicities down there? Don't you have ongoing, do you have ongoing star formation down there, so you're expecting a much wider range of metallicities?
Well, probably you have some more massive black holes, yes, maybe 2020, but so what?
Well, because 1010 you can't see. You can't see out of the Milky Way with 1010. Or you just barely, you can get to the Andromeda. You need the massive black hole. You need the massive black hole. I thought you said 1010. 2020. Yeah, those you can do. Okay. Yeah.
Okay, any further questions? I have one.
Okay.
Out of curiosity, within 15 megaparsec of here, how many globular clusters are estimated to be? Order of magnitude, 10 to the 7, 10 to the 10?
No, not that many. I'm thinking 10 to the 5 might be excessive. 10 to the 4. 10 to the 4, 10 to the 5.
Including the video cluster, you mean?
Yeah. Yeah. I mean, out to, well, 15 megaparsecs gets you kind of to the leading edge. So yes, like I said, that one, it has 6,500. I think, is it M87's got something like 10,000. The Andromeda's got a couple hundred, 300, I think. Milky Way, we've only got 150. Yeah, so I'm just doing a very, I mean, the number, don't quote me on it, but I'm doing a quick estimate saying probably on average there's maybe at best around 500, and then there's probably around, maybe about 1,000 galaxies.
Yeah, Sanjay, have a question?
Yeah.
Even when we can observe the chirp for a very long time, we can measure distance only to within a factor of 50% accuracy.
Okay.
You know the reason for that.
Right.
So I wonder whether, given that uncertainty, you will probably be able to measure omega dot by 1 billion.
Well, actually, remarkably enough, going back here, let me find the image I want. And probably it would be smarter for me to just have waited. There. Well, no, I haven't done that, but if you look at this last box here, this is a measure of chirp mass versus log frequency, and you see that kind of arbitrary cut there? That's when they chirp through the Lisa band and leave the Lisa band in a year. So they're out before a year, at which point you're definitely chirping through more than one bin. And that's when you start, and within a year you're out of the bin.
So for that population of frequency, very high frequency,
Yeah, it'd be possible, but then we're looking at, the problem with that is the numbers go down. The density goes down like the period to I think the 8/3. Yeah. Yeah. So it's a possibility. I'm not saying you're going to guaranteed get those distances, but if you can, you've got some very good possibilities.
Does the acceleration in the globular cluster screw this up?
Well, no, these have been ejected.
Okay.
So they're at best they're halo systems. So they're just kind of floating around their host galaxy. So you're not going to have to worry about a changing, like as if they were in some triple system or something like that. And that's part of the reason why I like the globulars is because, like I said, they're clean.
Many said that. How much will the first figure change if you get money from Americans and you can have a third dart?
Basically, personally, I think if you got money from the Americans and you get the third arm, then that makes the signal-to-noise ratio of 8 reasonable, because now you've got, you know, adding them in quadrature to get the signal-to-noise. Because to my mind, signal-to-noise of 8, you're not going to, you know, it's sort of like what Satya said. You're going to do pretty crappy parameter estimation with a signal-to-noise of 8. Yeah. So the third arm basically makes this a much more reasonable one. I should probably take it up to a signal-to-noise ratio of 15 if you're just doing a single.
Say larger or equal, is it larger?
Right. Okay. Yeah. Yeah. So larger, but that's part of it. Is this is just, is it detectable?